In the same way that we did kinetics in normal and tangential components, we also do force analysis in normal and tangential coordinates. So if we have a particle moving along a curved path, we might have we have a particle here. And remember that in normal and tangential components, we would have an acceleration here that was tangential to the motion. So we can denote this as the mass times AT. And then we also had the normal component of acceleration, so we could denote this as mass times AN. And this will be equal to the summation of forces in those two directions. So you would have here the summation of forces in the tangential component, and then you would have the summation of forces in the normal direction. A quick reminder that this AT component represents the change in magnitude. So this was actually the change of the speed itself of the velocity vector, so change in magnitude. And this normal component was the change in direction. And it always points towards the center of curvature, which means the summation of the forces in the normal direction also point towards the center of curvature. So it actually goes against physics for those forces, the normal forces, to point against the center of curvature, because then your particle would be turning in that direction. Now let's look at an example of how this would work. I'm just going to move the screen up. Make this a bit smaller. So this question says that you're looking at a turntable, and it's observed during rehearsal that trunk B starts to slide on the turntable 10 seconds, so our time is 10 seconds, after the turntable begins to rotate. Knowing that the trunk undergoes a constant tangential acceleration, so acceleration tangential is equal to 0.24 meters per second squared, determine the coefficient of static friction between the trunk and the turntable. So it's asking for the coefficient of static friction. So in this case, for these types of problems, the force T and the force normal, so the tangential force and the normal force, are the friction forces. That's what we're trying to capture here. So I'm going to start by drawing the turntable from a top view. So if I draw a turntable from a top view, the trunk, I'll put it here. And now I'll draw unit vectors. So the tangential unit vector would be going tangent to the path of motion. So this would be our ET. And then we would have our normal direction here. This would be our EN. So our forces will be going along, sorry about that, I accidentally changed the page. We would have the force going upwards, so we'd have the force tangential going in that tangential direction, and then we would have the normal force here. The actual force, the sum of those two vectors, would be somewhere in the middle. This would be the sum of force, and this would be the force of the friction, the total force of friction. But when we break it down into components, we have here the tangential force and the normal force. Both of these add up to make our total friction force. That's the friction force that we'll use to find the coefficient of friction. So if we look at the tangential force first, so we have the summation of the force tangential is equal to the mass of the particle times whatever the acceleration is in that direction. So this would be acceleration tangential. But how do we figure out what the tangential acceleration is? Well, if you remember from the previous chapters, we know that the tangential acceleration, this is the change of speed with respect to time. So it's the actual change of speed that's captured with the tangential acceleration. So if we're looking at the change of speed, and speed is just v, it's not the vector, it's just v, and v is the change in distance with respect to time. And distance for circular motion is usually called s. So s is our distance traveled. Note that this is not the vector, this is just the distance traveled. And our s would be equal to r theta. Now this equation is just the basic arc length of a circle. So arc length, if you have a circle, oh, that's terrible. Let me redraw that. So you have a circle and you're looking for an arc length. So say you're looking for this distance here, and this was s. S is equal to r theta, where the r is the radius of your circle and your theta would be the angle between. So going back to this equation, we have s is equal to r theta. So then the derivative of s would be your speed, which would be r theta dot. Because our radius isn't changing here. We have a circle. So d over dt of r is equal to 0 in this case. So when you do product rule, you're left with r theta. And then when you take the derivative again, you have acceleration tangential, because that's the change in speed, is equal to r theta double dot. So now we have an equation for AT. So I'm going to move the whole thing up now, so we're not going to see the problem anymore. Oh, let me just rewrite lower. So we have t equals 10 seconds, and we have AT is equal to 0.24 and mu s. So I'm going to move everything up here. So we have the summation of force tangential is equal to r theta double dot, which will be equal to our r was 2.5 meters times our tangential acceleration, which was 0.24 meters per second squared. So now we have a value for our tangential force, which is equal to 0.6 newtons. For the normal force, our summation of the force in the normal direction is equal to our mass. Oops, I made a mistake. Can anyone catch what mistake I made here? So I forgot my mass here. So we should have the mass of the block. So this should be times the mass of the block. And they don't give us a mass of, oh dear. They don't give us a mass for, I can't erase this in. They don't give us a mass of the block. So we just have to leave it there as an m. So the normal force will be mass times acceleration in the normal direction. And acceleration in the normal direction is equal to the speed squared over rho. In this case, we don't know the v yet, but we do know the rho. So can we figure out the v? Of course we can, because we have constant acceleration, and we know the acceleration. That's known, and we can use our constant acceleration equations to find speed. Our speed would be v is equal to v naught plus at. So our speed is equal to 0.24 meters per second squared times 10 seconds. So our speed is equal to 2.4 meters per second. So now we have our summation of force N is equal to 2.4 squared divided by 2.5, which was the radius, times m. So that's equal to 2.4 squared divided by 2.5 is 2.304 times the mass newtons. Now, the force of friction, I'm going to move this up just a touch. The force of friction is equal to mu, and we don't want it to slip, so it's mu s times the normal force. Now we can find the normal force, and to do that, I'm actually going to draw a different view of our turntable. So if we draw the side view of our turntable, and this would be our trunk here on top of it, the force here, the forces on our trunk would be the weight coming down, which is equal to mg, and you would have this normal force going upwards. So that means if we combine all the information we have so far, we have force of friction is equal to mu s n. Normal force is equal to mg, so this would be equal to mg. So then we also know that the force, the summation of our forces is equal to the force tangential plus the force normal. So to combine those, to add these vectors, we can't just add them directly because they're in different directions. So we would have our tangential force, which was 0.6 times mass squared, plus 2.304 times mass squared, square rooted, that's our sum of the forces, is equal to, oh, and I have a typo right here. I forgot to put my mu s there. So I'm going to just erase, I'm just going to erase this quickly. Oh, I don't know why that won't erase. So this would be times mu s up here. So then our sum of the forces is equal to our friction force, which is equal to mg mu s. When we do the math here, we end up with 2.38 m is equal to mg mu s. These m's cancel. Gravity is known, so divide by 9.81 means our mu static is equal to 0.24, and that's unitless. So in this problem, we actually don't ever find out the mass of the trunk, but the mass cancels out, so we don't need to know it. Shoot. Directions. So we